Right, good day everyone, or good afternoon, and it would be good morning, still good morning to Mike Ippen. And we'd like to welcome all of you to this session number 9 on water distribution. And as Mike will indicate to you what the plans are for week 11 and 12. And so over to you, Mike.
All right. So good afternoon, everyone. I'll be sending you the PDF of today's presentation. I'll do that through the chat in a minute as we go through that. Got a couple of videos on pumps. So today's pumps and motors, and really to highlight the need to know information for the exam. Next week will be operations, maintenance, and repairs. The exam has not a lot of questions on it, but there'll be some concepts that are need to know and reinforced for level 2. And then basically the plan, I'm not available for week 11 and 12. So week 11 will be a practice exam. So it'll be 50 questions. Takes about an hour and a half at the most, maybe an hour and 10 minutes. Maybe even 45 minutes if you've looked at the material. And then week 12 is review. And then hopefully you're able to go in and write your exams anytime after the 14th. So that should be good. So so I'll send the information for the pump material, pump presentation today. And also we've got another set of questions. So this week and next week. So between the questions that have gone out every week and the PowerPoints that you've got a really good foundation for both the practice exam and for the certification exam. So hopefully that'll stand you in good stead and you'll do well for the exam. So hopefully that works for everyone. So we've got quite a bit of material. There's a couple of videos too. A couple of them are a little longer than the last ones, but they really focus on the types of questions that are asked in the certification exam. As I mentioned earlier, a lot of level 1 and a ton of overlap on level 2 water distribution certification exams are recognizing what the component is or the principle, as opposed to applying it and doing analysis of it. So on that note, so it's like knowing what an impeller is and its function as compared to a bearing or a packing gland. So recognizing the basic functions and which type of pump fits best in which application. So it's really recognition and application as opposed to analysis at level 1, level 2. So having said that, enough of that. Let's go right into today's presentation. And as I say, I'll break off for a couple of videos along the way. So let's get this show on the road. I know it's late afternoon for you, and so I really appreciate you hanging there for the sessions. So we'll talk a little bit about motors. More of the focus on the exam is parts of the pump, so we'll cover that off. A little bit on motors though. And for those of you that work around pumps in a water distribution system or treatment plant, this should be a review, but basically we're hitting the high spots here for help basically for the exam. But when we're talking about a water distribution system, we're really talking about booster or inline pumps or pumping to a reservoir from a treatment plant or to an elevated water tower. So when we're looking at doing that, we need to have a motor, and we need sometimes called a prime mover. We have to get that energy and impart energy to the pump and then to the water column, right? And so think back to some of the hydraulics we've talked about, where we're really talking about adding energy to create head, whether that's in meters or feet. We need to have a vertical column of water sufficiently high enough to push water to all of the areas of our distribution system, and hopefully for 24/7. I know in your parts of the world there are water systems that are intermittent, and that could very well be. Usually there's two reasons for that. One is no power, and the other is not enough water. But in this case, power is the requirement to be able to move water, to create that energy to lift water to a higher elevation. And typically to do that, we're looking at motors with three-phase current. So alternating current, three-phase motors, and for a couple of reasons. First of all, when we're looking at choosing a motor for a specific pump or a specific application, we have to make sure that it is rated correctly for the incoming voltage from our supplier, power supplier, our hydro supplier. And then the horsepower is the power that then will impart that energy through the pump into the water column. So we have to establish what our needs are in any one area of the water system. So voltage ratings are consistent with what is our source. And then the horsepower rating is basically what we want the pump to be able to do. For small applications, you may have single phase motors, and that's quite common and certainly for remote areas, rural areas, where it might be a direct DC power supply, so coming off a battery as opposed to a power grid. The key to remember, certainly for the exam, is that a single phase motor has no means of applying torque, which of course is what we're doing with a three-phase motor. So what we mean there is that we have to start the motor in another way. So we'll talk a little bit about that as we go on. With AC current, the other ability with a three-phase motor is that we can apply power through varying voltage supplies. So you can see there on the slide, basically everything from 230 all the way through to 600 typically, or larger as our power supply warrants. One of the key features about three-phase is because we're applying three wires to two different phases, we can actually not only reverse the flow of the pump by switching the leads, but we can also be in a situation where if we have a partial power failure, sometimes we call that a brownout, there's still power to the motor. And in some cases, unless it is prevented from doing so, a pump could actually run backwards, or it could heat up excessively. But the advantage really for the three-phase is the versatility of sizing a motor based on the power that we have, and also the ability to impart torque on our motor. Now, we're not going to go through all of this, but I would recommend, I'm going to send you the PDF. So this slide of just taking a look at the cutaway drawing and matching up the elements from the list that's on the left-hand side here. And the ones that basically show up for the exam is the shaft, number 27. You will see also bearings and where those bearings reside, right? So when you're looking at the legend on the left-hand side, you can see the different elements, so where the bearings reside, number 6. Also, if you've got the need to lift the pump and motor, I mean, you've got number 14, basically it's just a bolt through the frame of the motor. Number 17, the windings, because that's how the current moves through from the stator into the rotor and creates the motion of the shaft. We need to support the shaft with the bearing. So number 25 at this end. Typically, we'll see an inboard and an outboard bearing, which basically reflects the direction to the pump, the base, and so on. So take a look at the cutaway over time and just be familiar with the key. We're going to go through some of the key elements as well in the video I have for you. Remember, again, three-phase power. Once it's applied to the stator windings, we create an electromagnetic field. And because it's alternating current, it creates the flow, which is rotary. And we end up with the interaction of the two fields, turns the rotor, develops torque, which then, of course, we're not moving water at this point yet. All we're doing is spinning a shaft. We connect that to the pump, and typically with a, say, a centrifugal pump, which we'll go into, we then create motion of an impeller, and that converts that energy in velocity to energy inside the pump. But really what we're doing here is building a device that can turn a shaft. We have to support the shaft through the bearings. We have to make sure that those bearings are properly lubricated and balanced. But really that's all we're doing, is adding power to the pump that we can then actually start changing the hydraulic profile of our water column. So let's see here. Where's that video? Oops, I just want to make sure that I've got the sound set up for you. Yep. Here's a very short video on the motors that we use.
85% of the pump applications used at water utilities, with internal combustion engines used primarily for standby service. Single-phase motors are used only for low horsepower applications. Motors used in water treatment that are larger than 1/2 horsepower are generally three-phase and may be operated at 230, 460, 2300, or 4000 volts. The main three classes used are squirrel cage induction, synchronous, and wound rotor alternating current. Motors convert electrical energy into mechanical energy and heat. About 5% of the energy is lost in heat and must be removed quickly to prevent the motor temperature from rising too high. Motors are usually designed for an ambient temperature of 104 degrees Fahrenheit, so ventilation air should be a lower temp. Care must be taken not to obstruct airflow around motors. Motors installed outside need to be protected from rain, dust, and wind-driven particles. Small motors are usually started by directly connecting line voltage to the motor. Large motors are typically started and stopped using a reduced voltage motor starter. A motor starter includes a main disconnect switch, fuses or a circuit breaker, motor protection for temperature, unbalanced current and other parameters, and provisions for remote operation. Remote and automatic controls eliminate the need for an operator to be near a pump to operate it. Systems are also furnished with malfunction alarms that will alert the operator if preset limits are exceeded. Detailed records should be maintained on all pumps and motor equipment for use in scheduling maintenance and evaluating operation. Water utilities should keep.
So one of the key things in here to look at is with the three-phase. You mentioned that obviously maintenance is important and dust is a big issue with motors, and heat, right? We've got to keep the motor within the manufacturer's recommended operating range for both temperature and overall air quality. So there may be filters in the room where the motor is, certainly ventilation to keep temperatures down. The other key thing that will show up on the exam is the difference between a single phase requiring direct power to actually create the rotation versus in three-phase where you have the ability through the motor over here to actually create torque. But because there is such a huge draw of power when that first switch is turned on, that pump manufacturers will pair them with motors that have various capabilities. For instance, a variable speed drive that starts at a much lower RPM, right? Rotations, revolutions per minute, and ramps up, or what's called sometimes a soft start, so that that minimizes the amount of voltage that must be applied to the motor in order to turn the shaft. So you can see in this variable speed, sometimes known as a VFD. Because otherwise, the amount of energy required to turn a 500 horsepower motor may actually trip either an overload switch or actually the main breakers and pull down the power supply. So it's a way of soft start, slow start, so that the inrush is not so great as to cause electrical malfunctions. And that may show up on the exam. Be comfortable with what VFD stands for. It's not the Vancouver Fire Department. It is variable fixed drive, or a variable or flow drive sometimes. Mostly it's a variable speed starter for the motor. And there's an example on the panel of the 3 phases that are brought into a starter panel. And then allowing, through this soft start, the ability to turn the motor on without causing problems back with the supply of electricity. So across the line start means basically using the direct connections, but mostly for, again, as it mentions here, much smaller motors, so they don't have such a high draw on the current. Because, yeah, as the slide mentions, the inrush, or the actual draw of current when a motor is called for, and again, you think about a remote operated system, a switch or a level recorder or a float switch turns on, tells the motor to turn on because the reservoir is low and needs to be refilled. Well, that could cause that inrush, and depending on the time of day, the power utility may already be stressed out based on everybody else using power. So we try and minimize that. We also are trying to avoid high temperatures across the windings of the motor, because that can cause the motor to fail. So yeah, reduced voltage, so a variable speed control, or a slow start that can then minimize the actual inrush of current. A couple of quick review questions before we move on to pumps. The correct way to clean an electric motor. Basically what they're looking at is, again, the enemy of an electric motor is dust and high temperature. So we do not want to add water or soap. We're looking at just blowing off the dust with compressed air. The amount of voltage is essentially, so this was from the electrical section. We're looking at, again, the voltage equivalent to pressure. How much is available? So we have to size up our motor to meet that power supply. Larger applications typically draw from they're looking for here, a 3-phase power supply, right? As opposed to single phase. Squirrel cage is a type of motor typically used in 3-phase applications. Okay, so very brief. There are a couple of, well, we'll have some examples in the sample exam on motor questions. If you want, there's a couple of videos, they're quite long, and they're more designed for water treatment plants, but there are some issues or videos on that. So motor rotation on a 3-phase can be reversed by basically swapping 2 of the 3 leads. Okay, and that may show up on the exam. All right, so the bulk of today, we're going to talk about pumps, because they really become critical devices in our water system. So why do we need to pump? Well, depending on the topography of your utility, we can't use gravity all the time to supply sufficient amounts of water under sufficient head, and with enough pressure to meet all of the service demands. So you think about when we were talking hydraulics, we were talking about the different requirements to supply water. It has to be in enough volume for all of the different uses, domestic, emergency, agricultural, industrial, and so on. But it also has to be at sufficient energy to even make it to all parts of our system. And so when we can't do it with gravity, then we have to pump. Now, of course, that becomes expensive for utilities. If the requirement to pump to elevated storage or to boost the grade line within the distribution system, then that's reality becomes a 24/7 operation. So we need to try and minimize how many pumps we have to use. And then we're going to talk a little bit about which pump to choose and also how to size it correctly so that when it is in use, it is the most efficient for the application that the utility requires. So there's more than 2 types of pumps used in water distribution, but these by far are the most common. And there is a real divide in the distribution system about the application. So we'll talk a little bit about velocity. Sometimes they're called kinetic pumps as opposed to positive displacement pumps. And when we did the meter session, we talked about positive displacement meters, the idea being a fixed volume of water moves through a fixed meter chamber, measuring chamber, and that creates a known volume. Well, it's much the same. A positive displacement pump actually, through the motion of its gears or whatever configuration of its measuring internal chamber, can now move a fixed amount of water through at certain head based on the size of the pump itself and the motor that's connected to. So on the left, the picture there is a peristaltic pump that's been disassembled. In the middle here is a centrifugal velocity pump, and then a jet pump that we can that has a little impeller inside as well. So we'll show you go through in detail, and try and hit the high points for the exam. But remember, velocity pump is one style or type of pump as opposed to positive displacement. There are 2 different classes of pumps in our system. So let's start with velocity, sometimes called kinetic, and often just in shorthand we call them centrifugal pumps. And we'll talk about that as well. But very versatile. We use them because of the wide range of operating parameters that we can apply. So both in terms of how much energy we need to apply to the water column and also how much flow. So how much water, the volume, and what pressure, how much energy we're imparting into it. They all work by converting the water column from velocity to pressure, and that's why they're called velocity. The spinning impeller accelerates water. So we speed up water moving within a confined space within the pump casing, and it is as that water is spinning through the casing and it hits the side of the casing, and we specially shape the casing for that purpose, it converts the high speed water into pressure. The other advantage about one of the things that makes velocity pumps so versatile is that we can actually turn them on, start them against a closed valve, which is very important when we are dealing with minimizing water hammer, things like that, or when we're going against wanting to use, if we don't have, say, a variable speed drive that can slowly ramp the motor and the pump to full operating condition. We do that by closing the discharge valve, start the motor, which starts the pump, and that is okay. It doesn't damage the pump. Whereas if we did that with a positive displacement pump, it could ruin that pump. So you can see on the drawing there, basically, most centrifugal pumps that we're going to see are what we call a radial flow. So, and when we think radial, we're really talking about radius. So radius of a circle. And you can see on the sketch that basically we're pulling water in through the eye of the impeller, and the motion of the impeller spins it out and discharges it at 90 degrees. We put that impeller inside of a volute. Sometimes you'll hear people talk about a snail shell because of the shape. It's a spiraled casing, which then creates this higher pressure because of how we push the water. The impeller pushes the water against that casing. So we'll get into some of the types of velocity pumps, but I've got a video I would like to share with you, because this guy does a really good job explaining the oops, here, let me have to close this out first. He does a really good job explaining the principles of them. So let's see if we can bring Adam here.
And today I'd like to talk a little bit about centrifugal pumps. Centrifugal pumps are definitely one of the most common machines in the industrial landscape. In fact, they're second in number only to electric motors. And when you consider that electric motors are used to drive centrifugal pumps, it's safe to say that the lion's share of energy usage in the world goes towards pumping fluids with centrifugal pumps.
So before he goes on, it's a good example of the motor, the shaft. So the shaft inside the motor is going to be supported on a bearing. This is the coupling. This will be a frame-mounted assembly because there are actually two shafts. There's a motor shaft, and then the pump shaft you can actually see through here. He's cut away some of the casing. So there's actually two shafts connected by a coupling. And so the exam might ask, you know, the purpose of the coupling, and of course it's to be aligned so that it's true, so that there's no distortion. As the motor turns the shaft, it turns the shaft on the pump. And so the shaft for the pump passes through into the casing, have to seal it to prevent water from escaping. So the seal will be either a mechanical or a packing type seal, the mechanical. This is the pump casing. The impeller is situated tightly inside. You can just see the wearing, which he's going to talk a little bit about and we'll cover off inside. And then again, the shaft moving through. So this is basically a split case centrifugal pump because it's split along the axis, which is parallel to the shaft.
So if you're an industrial maintenance technician, mechanic, machinist, you'll come across these machines at some point in your career, so it would do you some good to know how they work in the first place. In general, a pump is a machine which converts mechanical energy into the kinetic energy of a pumped fluid for the purpose of transporting that fluid from one point to another. But in order to be classified as a centrifugal pump, a pump needs to have two unique components. The first is a rotating disc with curved blade-like veins on it called an impeller. And the second is a specially shaped pipe called a volute casing, which contains the impeller and the pumped fluid. In the most basic sense, here's how a centrifugal pump works. Fluid enters the pump at the center of the impeller, called the suction eye. Friction between the fluid and the surface of the rotating impeller causes the fluid to rotate. Think about it like this. Just like the friction between the road and the rubber in your tires propels your car forward, the impeller gains traction on the fluid as it spins in contact with it. The rotating fluid is thrown to the outside of the impeller by centrifugal force, a phenomenon which causes objects revolving around a center point to move away from the center. This is how the fluid picks up kinetic energy from the impeller, and this method of energy transfer by centrifugal force is why these pumps are called centrifugal pumps. The amount of energy actually added to the fluid is dependent on three factors: the density of the fluid itself, the impeller's speed of rotation, and the impeller's diameter. From the impeller, the fluid is released into the chamber of the volute casing and directed around to the discharge outlet, and ultimately into the system. Let me take a minute to set the record straight. A very, very common misconception is that these curved vanes help to move fluid by cupping it and pushing it through the pump. So then the correct direction of rotation for this impeller would be clockwise, right? Well, that's not really what the vanes are there for. The vane's purpose is to conduct the fluid along the smoothest possible path as it travels through the pump. Backwards curved vanes help to stabilize flow conditions at high speeds and reduce demands on the motor. The correct direction of rotation for this impeller is actually counterclockwise. And you can always tell the correct direction of rotation of an impeller just by looking at the way that the vanes are curved. It's important to add that because of the way that centrifugal pumps impart energy to fluid, the impeller must always be fully submerged and in direct contact with the pumped fluid. As we can see from this little light-duty pump, a centrifugal pump will not pump air, and it will not suck fluid through piping like a straw.
So that basically talks about, we talked about this with hydraulics, the need to ensure that there is prime against the inlet of the impeller. So he's going to talk about flooding. Sometimes we call it flooded suction, where the water, there's sufficient energy in the system to force water against the impeller, the eye of the impeller, at all times, even when the pump isn't running. If not, that's why we would need, say, a foot valve or a check valve of some sort to hold water against the eye of the impeller, because otherwise the pump will become airlocked and the pump will continue to turn because it's getting the signal that it needs to boost the pressure or move water to a reservoir, but there's no water moving through. And you can see that in the video, where there's actually an air gap there.
So before the pump is turned on, the casing must be flooded with fluid, a process known as priming. And during operation, there must be a sufficient amount of available fluid under positive pressure at the suction inlet of the pump to replace the fluid which is being discharged. This is usually accomplished by placing the pump below the fluid level of the source tank. If the pump is ever starved of fluid, certainly the pump's performance will be affected, but it's actually more serious than that. It's possible that the pressure at the suction eye of the impeller will drop below the vapor pressure of the pumped fluid. If that happens, then the fluid will effectively boil. Little bubbles will form, travel partway through the impeller, and then collapse at supersonic speeds like little bullets, taking bits of the impeller along with it. This is a condition known as cavitation.
And that will be on the exam. So basically, creation of vapor bubbles inside the impeller that, as the impeller is turning, they explode on the outside edge and then can cause damage to the impeller and to the pump itself. And it sounds like that the pump, some of you may have experienced this if you've got these kind of pumps, the centrifugal pump, it'll sound like the water pump is actually pumping sand or gravel.
And a pump that's experiencing cavitation is not long for this world. I know that I use these little water bubbles in my animations to illustrate the fluid path through the pump, but actually that kind of entrained air or any other gas is the worst case scenario for a centrifugal pump. Let's talk about the volute casing. Volute refers to the shape of the casing. A volute is a geometric shape defined as a spiral with an ever-increasing radius, like a snail shell. Hopefully you'll notice that the volute chamber on this pump doesn't stay the same size all the way around. It actually increases in area closer to the discharge outlet. And at the point where the discharge outlet begins and the volute chamber sort of starts over, there's a wedge-like protrusion called the cutwater. The cutwater physically separates the discharge outlet and the volute chamber, and it ensures that fluid actually leaves the pump instead of just recirculating over and over again inside of the volute chamber. Now, the increasing area of the volute chamber is essential to the function of the pump because that's how the pump develops pressure. We've talked about how the impeller imparts kinetic energy to the pumped fluid. And when I say kinetic energy, think of it as the speed of the fluid flowing through the pump. But flow speed is only half the equation. A pump also needs to be able to develop sufficient pressure to meet the requirements of the system. Usually this involves overcoming gravity by raising fluid from a lower elevation to a higher elevation and overcoming the resistance or friction of the pipes which conduct the fluid. Think of pressure as the ability to accomplish a task, and flow speed as how quickly the task can be accomplished. To build pressure, the pump has to do some science magic to convert kinetic energy into pressure energy. As fluid travels through the volute chamber, it actually starts to slow down as the area of the volute chamber increases. That's because flow rate, or the amount of fluid which is moved during a given length of time, is dependent on two factors. One is the speed of the fluid, and the other is the size of the chamber through which it's moving, meaning how much of the fluid is moving at that speed. If the flow rate is constant, then an increase in the size of the chamber would result in a corresponding decrease in the speed of the fluid.
And that's kind of what we talked about with the Venturi meter, right? We change the cross-sectional area. So by making, in the Venturi meter example, we shrink the area, and that flow so the velocity increases and the pressure goes down. Here's the opposite. We're increasing the cross-sectional area, which then slows down the velocity and converts that into higher pressure. So it's actually the volute. So on the exam, it's not the impeller that creates the pressure, it's the cross-sectional area of the volute.
This is where a guy by the name of Daniel Bernoulli comes in. He discovered 300 years ago that there's an inverse relationship between a fluid's velocity, or speed, and its pressure. Meaning that if the velocity goes up, then the pressure comes down. And if the velocity goes down, then the pressure automatically goes up. So as the fluid is slowing down in the ever-expanding volute chamber, it's also picking up pressure. So that by the time the fluid reaches the discharge outlet, a great deal of its kinetic energy has been transformed into pressure energy. And I think that's a pretty amazing little trick. Well, there's your introduction to centrifugal pumps, their function, the main parts.
And so that was really why they become such a versatile pump for our water systems. Oops. Because we can now change the type of pump we use based on what we need that pump to do. So we know that the action of water entering the suction eye, as long as no air gets in, will be, by the spinning of the impeller, thrown out into the wall of the casing, the volute. And do recognize that the volute is the casing, sometimes called a snail shell. That will show up on the exam. And it's that action of hitting the casing and traveling along the casing to the discharge that creates the pressure. So we can then say, well, we sometimes need higher volumes than pressure. And here's an example of an axial flow pump. And so the name of the pump is based on the direction of the water travel. So there's our shaft. So axial flow means we're actually going to pull water up parallel to the shaft, and our impeller is here. more like a propeller, in this case, open vanes, and then we pull water into the outlet pipe. So here's a situation where we need lots of water, but we don't necessarily have to push it very high. And remember, when we're talking about pressure, we're always talking about the vertical column of water that we're creating. So how much energy are we adding? So as you can see, the third bullet, high flows but lower head. Mixed flow, this is a combination. So a mixed flow pump has features of both the radial flow, which is this is radial flow, right? 90 degrees to the input from the impeller. Axial flow, parallel. So 90 degrees, this is radial flow. The shaft and is horizontal and we're pushing it vertically, so 90 degrees. Axial flow, we're following the actual shaft itself, parallel. Mixed flow does a little of both, and you can see the bowl is actually shaped kind of at a 45-degree angle. The impeller is here, our water comes up, and so behaves as a little bit of both, partially thrown against the bowl or the casing, but it's not a full volute, and then travels up along line shaft. So common in wells, and also common where there is, it's not perfectly clean treated water. I mean, wastewater situations as well. We can also, if we need to do both, we need high head and high flow, we can actually stack impellers one on top of another. So here's an example of basically the shaft and the eye of the impeller, the vanes turning, and basically throwing out discharge into, you know, the water column. We can actually stack them and create a vertical turbine. So there is an impeller at every bowl here, inlet 1, 2, 3. So this would be a 3-stage turbine pump. So it does both. It can actually bring high flow into the discharge. It can also increase the pressure, because think about it, impeller turns, converts the water striking the bowl or the casing, converts from speed, kinetic energy to pressure. It then enters the eye of the next impeller, turns, and that speed converts what is already an increased pressure head into a higher pressure head, and so on and so on. So we have what we call a multi-stage centrifugal pump. So very typical application, you would see, say, suspended into a reservoir, into a concrete or steel tank that is full, and we're pumping further up into a higher elevation somewhere else in the system. And a jet pump, much smaller application typically, low lift, water level. We have an inlet, a foot valve to create prime, so there'll be a little impeller here. But what we do is the jet goes through the ejector and then creates a partial vacuum that helps almost reverse siphon the water into the discharge, typically for much smaller applications, so including wells. So those are the key concepts on velocity for the exam, right? For the velocity pump, the impeller, the volute, the actual flooded suction, and we'll do some review of this in a minute, and then the different types of velocity pumps, but all work off the same principle, basically. And you won't have to remember Bernoulli's equation or anything like that either for the hydraulics or the pump section. But what we're looking at is the ability to move water, to impart energy at a very economic cost in terms of power consumption and maintenance for the pumps. So let's talk a little bit about positive displacement, the other main classification. Here's an example of a rotary or screw pump that lifts water based on a fixed volume from one elevation to the next. So key here is we're not typically using them to move volumes of water in the distribution system, but lots of times we need smaller versions of pumps either to add chemicals or to draw water out to sample in various places in the distribution system. So a couple of examples of positive displacement pump, and they may have different construction, but the principle is the same. On a reciprocating or on a piston pump, basically here's the piston in dark blue, a shaft or a cam turns, and the piston moves back and forth, and every time it pulls back, water is pulled into a chamber. When the piston closes, water is pushed out. Then the cycle is repeated. A fixed amount of water, or any fluid really, is brought in, and the cycle repeats. And it can do this at very high rates of speed, typically though with quite small volumes of fluid. Another example of a positive displacement is a diaphragm, and a lot of our trash pumps are diaphragm style. But again, the diaphragm is the piston. The piston is basically just like the piston in a car engine, but traveling back and forth on a shaft, and it's each rotation that creates movement through the pump. So there's the same with the diaphragm. So every move, every cycle of the diaphragm, either alternating pulling fluid in or discharging it back out. Here is a rotary, sometimes called peristaltic pump or a gear pump. And basically same, the rotation of these vanes or gears actually helps push the water through a very small chamber. So it pulls water in through the inlet. These rotate, and as they rotate, they push water, they impart some energy to push it through the discharge side of the pump. Before we get into the operation of that, I want to show you a video. Same dude. He's got a couple of good series. So if you're on YouTube, this guy has some really good, let's see, next one. So let's talk a little bit about positive displacement pumps.
The Machine Tech video blog, and today I'd like to talk a little bit about the different types of positive displacement pumps. At first glance, there seem to be so many unique designs of positive displacement pump that it can be a little confusing. And it really wouldn't make a whole lot of sense to try and cover every single possibility in this one video. But what I have tried to do is to break it down into 9 basic mechanisms. At the heart of any pump, you'll find one of these mechanisms. I've also tried to show a real-world example of each different type of pump. Each basic mechanism falls within one of 2 categories based on what type of motion it utilizes. We have reciprocating and we have rotary. Reciprocating pumps are the first category. Every reciprocating pump utilizes some kind of expanding and contracting chamber and a series of check valves in order to draw fluid into the pump and then direct it out into the system. To illustrate this concept, let's take a look at pump number 1, the piston pump. The mechanism consists of a reciprocating piston inside of a cylinder with check valves at both the inlet and the outlet. When the piston is on its suction stroke, which is the upstroke in this case, the chamber inside of the cylinder expands, the pressure drops, the check valve on the suction side opens, and fluid is admitted through the inlet. By definition, check valves permit flow in one direction only, so they help to prevent backflow and direct the fluid through the pump. As the valve on the suction side of the pump opens, the valve on the discharge side closes. On the discharge stroke, which is the downstroke here, the piston pushes on the fluid in the cylinder. The pressure rises. The suction valve now closes, and the discharge valve opens to release fluid into the system. Here's an example of a common piston pump called an axial piston pump. This pump is a tad more complex than our little demonstration, but the pumping action is generated in exactly the same way. The axial piston pump has multiple pistons equally spaced on the end of a rotating angled plate. As the plate rotates, the pistons are driven into and out of their respective cylinders. You can clearly see the motion here. Like most reciprocating pumps, piston pumps are relatively efficient, and they're capable of generating very high pressures. Pump number 2 is the plunger pump. Plunger pumps look very similar to piston pumps, but they work a little differently. Unlike a tight-fitting piston, a plunger fits loosely in its cylinder. Just like when your bathtub overflows because you filled it too full with water before jumping in, the physical mass of the plunger alters the size of the chamber and displaces the fluid.
And when we were doing hydraulics, showed you the Africa Dev pump that's used in many places with no power, and it's basically the principle of a plunger pump. The handle is pulled up, and the plunger is dropped and then pulled back, and it helps displace the water in the column and brings out a fixed amount, basically the same amount of water as the area and volume of the plunger itself, and that fills the buckets or containers at the surface.
This is a triplex plunger pump, which uses 3 staggered plungers for smoother flow delivery, but it is otherwise the same as our demonstration. Pump number 3 is the diaphragm pump. Unlike a piston or a plunger, an elastomer diaphragm is flexible. When it flexes, it changes the volume of the chamber, causing fluid to be drawn into or pushed out of the chamber. Our example is an air-powered double diaphragm pump. The pump is essentially 2 diaphragm pumps oriented back-to-back with the diaphragms linked by a connecting rod, so it can pump on both strokes. One unique property of the diaphragm pump is that it doesn't require a seal, because the wet and dry sections of the pump are completely separated by the diaphragm itself. The second category of positive displacement pump is the rotary pump. All rotary pumps utilize some kind of a moving chamber that traps fluid and carries it from one side of the pump to the other side. To illustrate this concept, let's look at pump number 4, the gear pump. Actually, this configuration is more properly called an external gear pump. The mechanism consists of 2 rotating gears, one driving the other, inside of an oval housing. At the suction inlet, fluid is trapped in a chamber between the gear teeth and the inside wall of the housing. The rotary motion moves the chamber from one side of the housing to the other side. And as the gear teeth rotate back into mesh, the chamber is closed, forcing the fluid through the discharge outlet.
So you can see very efficient, but not great for moving high volumes of water. So if we had to boost water pressure from one neighborhood to another, or move water to fill a reservoir, this would not be practical, even in a large size, compared to the centrifugal style pump. But if we have to add small amounts of water or chemical into our system, then they could do that very well and very efficiently.
Another configuration of the gear mechanism is the internal gear pump. In this type of pump, an outer gear in a circular housing drives an offset inner gear. The gears are separated by a crescent. Fluid is trapped in one of two moving chambers, between the inner gear and the crescent, or between the outer gear and the crescent. As with the external gear pump, the rotary motion moves the chamber from one side of the housing to the other side, and as the gear teeth rotate back into mesh, the chamber is closed, forcing the fluid through the discharge outlet. Pump number 5 is the lobe pump. Lobe pumps function very similarly to external gear pumps, but the rotors are driven independently by external timing gears. The rotors have 2 or more lobes, and the moving chamber is formed between the outer surfaces of the lobes and the inside wall of the oval housing. As one of the lobes rotates back toward the center of the housing, the tight clearance between the lobe and the other rotor closes the chamber and forces the fluid through the discharge outlet. Pump number 6 is the vane pump. A vane pump rotor has slots in it for sliding vanes. Centrifugal force flings the vanes out to contact the inside wall of the circular housing, forming a sealed chamber. Since the rotor is offset in the housing, the vanes extend and retract during rotation. The chamber increases in size at the suction inlet, drawing fluid in. At the discharge outlet, the chamber decreases in size, pushing fluid out. The nice thing about vane pumps is that they automatically compensate for wear because the vanes are constantly forced against the wall of the housing. Pump number 7 is the peristaltic pump. Peristaltic pumps contain fluid within a flexible hose. The hose is pinched between the rollers and the inside wall of the housing. As the rollers revolve around a center axis, they squeeze the fluid like a tube of toothpaste and move it through the housing to the discharge outlet. As with diaphragm pumps, peristaltic pumps do not require a seal because the fluid's completely contained inside the hose. They really excel at pumping high viscosity fluids with very large solids. I've even seen them pump whole cherries without significantly damaging them.
Oops. They're also very good at being used for water sampling because it'll pull water from a reservoir or a tank to sample and then release that water into a sample bottle. And with the tubing means that there's no spillage or potential for contaminating the sample.
Pump number 8 is the screw pump. Screw pumps can have a single shaft with large threads on it, but they usually have 2 or 3. The center shaft drives the other shafts like a screw or a worm gear. As the shafts rotate in the housing, fluid trapped in the gaps between the screw threads progresses along the length of the housing and is delivered to the discharge outlet. If you've ever seen an auger or a screw conveyor, this is pretty much the same thing. Our final pump is pump number 9, the progressive cavity pump. These bizarre little pumps may look somewhat like screw pumps, but they function differently. The rotor is shaped like a helix, and the housing is molded into the shape of a double helix. As the rotor rotates and oscillates inside of the housing, it forms a cavity which progresses along the length of the housing. Any fluid trapped in this progressing cavity is delivered to the discharge outlet. Well, there's your introduction to...
So I like the video because he goes into enough detail, certainly for an exam situation, but basically the key types of positive displacement pumps. And remember, the one factor that comes up on many of the exam questions is this is not a type of pump. No matter what type of positive displacement pump we're talking about, this is not the kind of pump that's operated against a closed valve. Whereas centrifugal pump, discharge valve closed, quite common for it to be closed when the motor is turned on, the signal received to start the pump, and as soon as the pump is at full RPM, the discharge valve will open. So safe to do. Whereas when you saw the cutaway of a plunger or a piston, if that check valve did not open, that piston is still going to shut and close that cylinder. It's got to go somewhere. It'll either go break a check valve or damage the actual pump itself. So positive displacement pumps are never operated against a closed valve. So a couple of examples that we saw. So the other key thing when we're talking about centrifugal pumps and operating them is we do not want water hammer or surges. And so that kind of gets back into closing the discharge side of the pump. So imagine we're moving water from one block to the next, but we have to lift it 20 meters. Well, if something happened and that 20 meters of head came back up against the pump, it could damage it. But by the same token, if that pump were to turn on and suddenly move that extra 20 meters of energy through the system, it could damage the discharge piping. So we try to minimize the water hammer. So we either do that by variable speeds, slowly starting the motor and winding the motor up, or by closing the discharge valve. And when we were looking at different valves, we looked at globe and butterfly valves as good candidates to be used in that application, because we can close them, put an actuator on it, and open it very gradually to smooth out the profile of the water column moving up into the elevated zone. Another key factor when we're starting or stopping a centrifugal pump, the pump needs to be primed. It needs to have a flooded suction, right? The pump, if the impeller is not submerged, then it will become airlocked and continue to spin and heat up. Doesn't necessarily damage it right away, but there needs to be an alarm or some signal back to the pump mechanics to let them know that the pump is not actually moving any water. And typically you'll see an air valve installed, sometimes at the top of the casing or at the discharge, to pull that air out so that the impeller stays primed. So a foot valve would be used to hold the prime, or we actually create positive suction by having the suction side of the pump higher than the eye of the impeller. Now, there will be questions about suction lift. In other words, how high can we lift water to the impeller? And this is basically just in meters or feet, but on the exam, typically it'll be in meters. So theoretical suction lift, 10.4 meters. You cannot. If you try to lift water higher than that, it won't work. But the reality is, because you have friction in the pipe itself and slightly different specific gravities of fluid based on where your elevation is above sea level, really we're looking at, we would not design a system that would have even close to 8 meters of suction lift. But in that 5 to 8 meters zone is where we would say, no, we don't want to lift it any higher than that. Otherwise, the pump will not operate. All right, so before we do this, I've got one other video from this same dude that I want to show you. So let's do that now, because we're getting into that portion of the slideshow. Where are you? There we go.
You a little bit about the different types of centrifugal pumps. When it comes to pumps, most operators only care about inputs and outputs. How much pressure does the pump generate? How much flow does it deliver? How much power is required to run it? But maintenance people need to know a few more details about the inner workings of these machines if we're going to be on the hook to keep them in good running order. We don't have time to cover the specifics of centrifugal pump operational theory here, but it was the topic of a previous video. Just as a refresher, centrifugal pumps get their name from the way they impart energy to fluid. When fluid enters the pump, it comes into contact with the rotating impeller and is thrown outward by centrifugal force. It travels through a specially shaped chamber called a volute and exits the pump at the discharge outlet. All centrifugal pumps share this basic operating principle, but there are a few possible variations among them. There are 5 primary design elements to consider: impeller construction, bearing configuration, orientation, driver mounting method, and the number of stages. There are a few special designs as well, but those will have to wait for their own videos. There are 3 types of impeller: open, semi-closed, and closed.
So there may be questions on the exam about the 3 styles of impeller. So we're not talking about propellers, all styles of impeller. And mostly what we're talking about is the desired energy we want to create, and also the type of fluid that is passing through the impeller. The dirtier or the more mixed the fluid, then the more open the impeller. So we typically reserve the closed impeller for distribution systems, and you'll see the semi-open or semi-closed and open styles for wastewater or on the raw side of treatment plants.
The simplest impeller construction is the open impeller, which consists of nothing more than a few curved blade-like vanes equally spaced around a hub on the rotating pump shaft. Large, unrestricted fluid pathways allow this type of impeller to pump fluid containing mud, leaves, twigs, sand, sludge, spray paint caps, dead birds, you name it. And that makes them ideal for trash pumps or this pump, which actually came out of a wastewater treatment plant where it was pumping raw sewage. It was necessary to handle gritty slurries with soft solids. And it even has special chopper blades just ahead of the impeller to help break down very large solids. Ooh. If the vanes are mounted on a backing plate called a shroud, then the impeller is a semi-closed impeller. Then it's a closed impellers, because the fluid is directed through very well-defined pathways. That means that more of the fluid is pumped out into the system and less of it is just recirculated around and around and around inside of the pump. Of course, the trade-off is that they can very easily get clogged with debris. Whichever style of impeller is used in a pump, it's mounted on a rotating shaft and needs to be supported by bearings inside of the casing in one of 2 ways, either overhung or between bearings. In an overhung configuration, the impeller is cantilevered on one end of the shaft and the bearings are offset to the other side. This configuration places the suction and discharge piping at 90 degrees to one another, with the inlet directly in front of the suction eye at the center of the impeller. This is why pumps with overhung impellers are more commonly referred to as end suction pumps. End suction pumps are abundant in industry because they're relatively cheap and easy to manufacture, but they do have one big disadvantage arising from the way that fluid travels through the pump. During operation, there's a zone of low pressure at the suction eye where fluid first enters the impeller, and a zone of high pressure at the outside rim of the impeller where the energized fluid is released into the volute chamber. This high-pressure fluid also has a leak path to the backside of semi-closed and closed impellers, which totally throws off the balance of pressure. The net effect is a constant axial force, or thrust load, pushing the impeller toward the suction inlet of the pump. You can compensate for this effect a little bit by installing beefier bearings capable of handling thrust loads, or drilling holes through the impeller shroud to allow for some pressure equalization. But neither of these are true fixes for the problem. A more effective solution is presented if the impeller is supported by bearings on both sides, called a between bearings configuration. Not only does supporting the impeller with bearings on both sides generally improve shaft support, it also means that many of these pumps can employ symmetrical closed impellers with double suction. Since there are identical low and high pressure zones on both sides of the impeller, this effectively eliminates thrust forces due to pressure imbalance. And this design has another key advantage. The suction and discharge piping are normally positioned parallel to one another on opposite sides of the pump. And the casing is split axially, so that just by removing some bolts and pulling the cover off, maintenance technicians can access the rotating assembly inside the pump without removing the whole pump from the system.
So this is what we would call a horizontal split case. And you can see here a couple of things. The volute, and you can see the shape, the wear rings. And so the wear rings are tight fitting between the volute and the impeller. And because it's a double-ended pump, you've got two wear rings so that water being pulled into either side, we've got the same close tolerances. And the wear rings are, you can see, made of an alloy or bronze. And they are meant to wear in advance of the actual casing. Because the casing, now you do have to take the pump out of service. Whereas you can replace the wear rings or the shaft sleeves here on either end without having to take the pump out of service. So you can see the shaft, the wear rings, and then the seals. And these you can see mechanical seals on either end which prevent leakage back from where the fluid is being pumped into the exterior, whether the pump station or back towards the motor. The motor is over here. So double end suction split case. And so when they say something is axially split, it just parallels the shaft. So a very versatile and very common centrifugal pump. And again, you can see this is a closed impeller, right, with shrouds on both sides of the vanes.
This axially split design is why pumps with impellers between bearings are more commonly referred to as split case pumps. Now, those are all pretty convincing reasons to go run out and get yourself a split case pump right now, but of course there has to be a disadvantage. Because the manufacturing processes and the sealing requirements for split case pumps are much more elaborate than for end suction pumps, they're also naturally more expensive. Next on the list of design elements is orientation, either horizontal or vertical relative to the pump shaft. Centrifugal pumps are usually oriented horizontally, but they can also be oriented vertically. Vertical pumps are used in plants where a reduced footprint and space savings are desirable. And you may also find one down at the bottom of a well or sump connected through a long line shaft to the driver above. This brings us to the mounting method of the driver, usually an electric motor. There are two options for transmitting rotational force from the driver to the pump, either frame mounted or close coupled. If the pump...
So that will be on the exam. So frame mounted simply means that we've got a coupling in between two shafts, as opposed to the close
frame mounted or close coupled,
which then basically the motor and the pump share the same shaft.
Coupled. If the pump and driver are two separate units, as they are here, then the pump and driver shafts will need to be connected by some type of a coupling. Now, couplings come in all shapes, sizes, and styles, but one characteristic common to all of them is that they require proper alignment of the shafts, and that can be a very finicky process indeed. To help facilitate and maintain machine alignment, the pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame mounted. For large, heavy equipment and for all split case pumps, frame mounting is really the only way to go.
It also means that alignment then becomes extremely critical, so that you saw him actually lifting up the pump with the shims. I'm just seeing if I can find it. There's the shim. So that the coupling here has to be perfectly true. and you see him working with the alignment tool to make sure both ends of the shaft are perfectly straight. The coupling, some of the couplings have large rubber gears that take up a little bit of misalignment, but over time, any slight misalignment between the two shafts will cause wear, which then can cause the bearing inside either the motor or the pump to fail.
The pump and driver are mounted on a common base plate, or in the case of units oriented vertically, the driver is mounted above the pump on a structural support called a C-frame. This type of pump and driver unit is said to be frame mounted. For large, heavy equipment and for all split case pumps, frame mounting is really the only way to go. A second option is the close coupled mounting method, in which the pump and its driver share a common shaft, with the impeller mounted overhung on one side of the driver shaft. In this case, there is no need for a coupling or any of the extra labor required to perform sensitive alignment procedures. However, since both the pump components and the driver components are supported on the same shaft just by the bearings in the driver, this mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps have...
The other thing about close coupled is that when you're looking at the close coupled, there's one less set of bearings required because there is only the one shaft. So the bearing coming out of the motor supports from the windings, then also supports the same shaft, of course, that hangs the impeller is hung on. But as he says, if you're doing maintenance on this type, you have to lock out the motor, separate it, pull it apart, so that you can actually access either the shaft or the impeller.
Driver components are supported on the same shaft just by the bearings in the driver. This mounting method is really only appropriate for small and medium-sized end suction pumps. Finally, a pump can be classified by how many stages it has. Most pumps have one stage with a single impeller and a single volute chamber. However, some pumps have additional stages connected in series to help boost the pump's discharge pressure. The idea is that the first impeller adds energy to the fluid and then feeds it into the next impeller, which adds more energy to the fluid, then feeds it to the next impeller, and so on and so forth until the fluid is eventually discharged into the system. Well, there's your introduction to the different classifications used for centrifugal.
So we talked a little bit about multi-stage. So remember, you're not going to have to remember how many stages. That's up to the utility. But by adding impellers and bowls or casings, we can increase the pressure to whatever it is we want without losing the flow characteristics that are so important for the utility. So a couple of this picture again, so you can see actually on this, to avoid airlock, there are some bleeding valves that can bleed the air out of both the casing and the suction side of the pump. The foot valve there, basically below grade, and a priming pump that can actually apply water to the inlet side of the pump. But again, either way, whatever operation you choose, the suction side of the pump has to be primed. Otherwise, you're just basically spinning the impeller and no air is being moved. No matter what type of centrifugal pump is installed, as an operator, it's really imperative that you learn what the manufacturer has recommended. Sometimes you can go, well, now you can go online and see the actual pump manufacturer, motor manufacturer, and download maintenance manuals. And if you don't, you should, so that you are on track with regular maintenance. It doesn't matter what the appurtenance is in a water system, regular inspection is critical, just so that you can document if there are any changes in performance. For instance, On March 24th, 2020, a pump cycle was 20 minutes, and this year it's 25 minutes. Well, that might suggest where? Inside the impeller or the casing. So we have to keep accurate records, but they should be always based on what the manufacturer wants. Bearing, seals, other moving parts require adjustments and or replacement. So that would be determined based, again, on the type of bearing. There are sealed bearings, and that's always seems to be a question on the exam. How often should a sealed bearing be lubricated or greased? And the answer, of course, is never, because there's no grease nipple. There's no way to do it. There have been famous stories of pump mechanics drilling into a bearing, sealed bearing casing, and installing their own grease nipples. No, don't do that. As opposed to a regular bearing on its own raceway, then it should be greased with the appropriate material. In other words, the grease should be approved for use in a water system, and it should be approved by that motor and or pump manufacturer for use on those particular bearings. Seals, depending again on the type of seal. If it's a mechanical seal, doesn't need to have any water moving through it to keep the seal, the rotating portion of the seal lubricated, as opposed to a packing gland on an older style of packing with a lantern ring. No, we do want water moving through, just dripping, so that the packing could be graphite or a hemp, braided hemp or a waxed hemp doesn't burn. So we always have to follow the recommendations of the manufacturer for the pump and or unit that we're looking after. And here's a cutaway of a typical end suction pump. And so let's start over on the right-hand side. You can see the flow coming into the eye of the impeller. So we've got a casing. We also have the volute. You can see the discharge here. So a radial flow pump, right? Our axis is horizontal, flow in at the eye of the impeller, and then the discharge at 90 degrees to it, right? The impeller will turn on the shaft. We also want to prevent leakage, and one of the main functions of the packing gland, and there's two really, but the key is we don't want fluid to leak out of the volute along the shaft. First of all, it could damage the pump itself, but you're not going to move any water that way. So you can see on the cutaway, this is a packing style of packing gland, of seal, with a lantern ring. Very difficult to see, but the lantern ring is right in between. So we've got three braids of different rings of packing on either side of the lantern ring. And then the packing gland follower ring stuffing box, this is squeezed on, that holds all of this inside, and you can see the actual body of the pump here, holds that inside. The lantern ring has a small orifice where we can actually bring water into the lantern ring, and then as the shaft turns, it pulls water underneath the rings to lubricate them. But because the rings of each of the separate rings are being pushed into place, we create a pressurized situation there, counterforce against the thrust coming from the actual pump chamber itself. So the packing gland prevents leakage from the pump, but it also prevents air from getting in, because it seals both air movement across the shaft and water movement. And then we've got, you can see here, the bearing that supports the shaft. Going back, here's the other bearing, set of bearings supporting the shaft all the way through, and then we tie on the impeller at this point here with the follower lock nut here. So that's the cutaway. So key pieces: packing prevents leakage of water and air either way. The lantern ring will actually allow water to be brought in to lubricate the rings of the packing. But this is a stuffing box packing gland style of seal as opposed to a mechanical seal. And then you can see the frame itself and then the bearings. All right. So key components for the exam, obviously the volute. And the volute is, remember, the volute is that portion of the pump that converts the high speed that's imparted by the impeller and converts the kinetic energy, which is the speed or the velocity of that moving fluid, water, and converts it to energy. So the impeller creates the velocity, the volute converts velocity to pressure. And we saw in the video 3 styles of impeller: open, semi-open, or closed. And again, based on the type of fluid and how much energy we're trying to impart into the water column. The impeller can wear, which means that either pump cycles will take longer, or could actually be that you can't pump water to the elevation that you desire because of wear. Wear rings will help that, because especially if there is, say, raw water and any potential sediment that you're pumping and moving through, the wear ring minimizes the wear. It also closes the tolerances between the volute and the impeller. So the wear rings can be typically brass or bronze, and we saw in that cutaway in the video that they're quite accessible, certainly on a split case. But again, they're designed to wear before either the case or the impeller itself is damaged. For pumps with closed impellers, then we're really trying to minimize the area between the impeller and the casing as it's spinning. We want to try and stop water from just circulating round and round and round in the volute. We want to move it to the discharge side. So those tolerances become really critical. So the wear rings help control the amount of water that is actually leaking from the discharge side, right, from suction to discharge. So as we're really trying to move as much water once around the volute and out into the discharge. The shaft, again, supported by bearings, and it's turned by the motor, and then we mount the impeller. And remember, there's 2 styles: the frame mounted, which means there's a shaft from the driver or prime mover, which we just for shorthand call the motor, and then a shaft for the pump. And they're coupled through a variety of means, but key that alignment is critical, right? So that we do not wear either the bearings or damage the pump or the motor. The shaft sleeves are replaceable sleeves, so they're typically pressed onto the shaft, also brass or bronze, and then where the packing goes through into the pump, and we have a shaft that's turning, we don't want to wear that shaft down, especially when we're tightening up packing or we've got the very close tolerances of a mechanical seal. So they turn on the shaft sleeve instead of the shaft, which means if we have to replace one, we do not have to go to the expense and time of machining a sleeve or a shaft, or actually replacing the shaft. The packing rings can be typically graphite, flax, synthetics, but remember, because they're controlling leakage, when we cut and place the rings, you saw in the cutaway, there are multiple rings. Well, we actually determine how long those packing rings are. We cut them with a box cutter, X-Acto knife, and then we carefully push them into place inside the stuffing box. But it's important, if we're trying to prevent leakage, we don't want the gap, the cut, where the 2 ends join, because we're basically creating a ring. So what we do is we stagger the rings 90 degrees. So if the first ring goes in with the join, the 2 ends touching at 3 o'clock, then the next set of packing will be 6 o'clock. The next ring will be at 9 o'clock. Then we'll put our lantern ring in and then repeat the same process so that the ring joints are staggered, and that helps prevent leakage. So that typically shows up on the exam. So keep that in mind. So the packing gland itself, so there's typically some sort of a follower ring that presses the packing into the stuffing box. Some sort of a gland that pushes the packing in. Now, if it's a mechanical seal, it's all built into the same unit, where we've got the front half of the seal turns with the shaft, and the other back half is fixed. Now remember, for a packing style of seal, they do leak, but we're doing that on purpose. We're tightening up the follower ring, the gland, and pushing and compressing the packing, just so that when we turn on the pump, there's water and there's pressure there. Water is leaking past typically 5 to 6 drips per minute. So it's not flowing, it's just dripping, and that way we know water from the lantern ring is moving across the packing and lubricating it. Okay, the stuffing box itself is that piece of the casing, so it's basically molded into the same piece that the volute is and the frame, but basically it's where we actually have the shaft leaving the wetted area where the impeller is. We need to protect that from leakage. The lantern ring is, yeah, it's basically perforated. It's basically cast so that it will allow water from an outside source, either the discharge or from a separate source, and pipe it directly into the lantern ring, so that when water is added, as the last bullet says, it creates a liquid seal around the shaft and lubricates the packing, so the packing doesn't burn. And because as the packing gets overheated, it will become brittle, it'll shrink, and you end up walking into the pump station one day and there is a flood because the packing has failed. Here's a shot of a mechanical seal. So and most new pumps are specified with that, and you can buy kits that will replace a packing style in some pumps with a mechanical seal, but it all depends on on the manufacturer of the pump itself. But as an alternative to packing rings, it again is placed over the shaft sleeve if the unit has a sleeve, and prevents water from leaking, but it also prevents air from getting into the pump and creating cavitation. The bearings, there's a couple of examples of bearings in their raceways. Again, support the shaft, but they're set up so that when the shaft turns, it minimizes friction loss. So again, we want everything to be efficient as far as the pumps go, because we're using electricity and paying for that electricity to turn the shaft in the motor. We don't want to lose energy because the shaft is harder to turn. So the bearings not only support the shaft, they actually help it turn by minimizing the friction. Bearings should not be over-greased, so we have to follow our manufacturer's specifications on that. Otherwise, the bearings run hot. They can actually damage the shaft itself or scratch and score the shaft. The couplings, we saw a couple of examples of them. If it's a frame-mounted type of motor / pump assembly, there's 2 shafts. They need to be connected and then properly aligned. And basically, here's an example of how we maintain prime. We're pumping so we've got a flooded suction, right? We've got static head, positive suction head. So positive suction head simply means that the water line, the elevation at rest, is above the eye of the impeller. Okay, so anytime that's the case, we have positive suction head. And this is on the suction side of the pump. Pump turns on. This is where we have to discharge it to. So we have an elevation called the discharge head, which is this line here to the center line of our reservoir. But we lose energy through friction based on the diameter and the size and age and configuration of this pipe. So when we size this pump and motor and we say, okay, we want to pump water to this point here, where the ball is here at the end of the diagram, we have to consider how much head loss. So we actually have to design the pump to actually pump above that point. And we can actually calculate that. Engineers calculate that based on the diameter of the pipe, the material of the pipe, and the distance and the configuration. And so the dynamic head is that total distance from discharge and head loss, considering all. But the other situation we have is negative suction, or negative suction head or lift. And here we have a situation where we're lifting water all the way up to this point, but we have to lift it to the eye of the impeller before the pump can do anything, right? So we have to pull that up. So our total suction head here, static head, and then discharge head. So now you can see this dynamic head as opposed to, oops, in this drawing was this discharge head and head loss here, this distance, because we basically have already got water to this point. We now have to move, our distance is much greater because we're actually lifting water. Just because it's on the suction side of the pump doesn't really matter. We still have to lift water this entire distance. So there's our total pump requirement here. So that's where knowing how your system is configured becomes really critical. So we're going to talk a little bit about a pump curve, and this is basically how we size our pumps and motors so that they actually do the work we need. And there'll be a couple of questions on the exam. So I'm going to quickly, I won't play the whole video, but I have a short video on, oops, I did that again. I have a short video on pump curves, but I'm just going to show you about 5 minutes of it. So just so we get the sense, you get the sense, and I'll stop at a couple of points along the way, how we determine, have we got the right pump and motor for the job that we need? And remember, the job is always moving water to a certain point of elevation. So we're adding head, and we have to figure out how much water we actually have to move at that elevation.
Head is shown on the vertical axis, and this is referring to pressure. So
this is a pump curve. Every pump that is you would order and buy for your water system has its own chart that comes with it so that you can see what it actually can do.
Often hear the term head pressure. We measure head in feet or meters, which doesn't seem correct considering we're talking about pressure, especially as you see the pressure gauges on the pump typically reading PSI or bar. The reason for feet or meters is that pump manufacturers only know how high their pump can push a liquid. They do not know which liquid your system will be pumping, and as each liquid has different properties, the pressure will vary depending on the liquid used. However, the height it can be moved by the pump will remain the same. For example, we have this pump which can provide 125 feet of head. If we use it to pump water, the pressure will be around 54.25 psi. But if we were to use it to pump milk, then the pressure will be around 56.15 psi. And that's purely because of the properties of the two fluids. Conversion between feet and meters of head is very easy. We have a free calculator for that, which you can find links to in the video description below. Why do we need to know head pressure? Pumps are usually used to move liquid to a higher region, so we need to ensure the pump can reach this elevation. As we pump liquid through the pipes and the fittings, friction will try to oppose the flow. This occurs from the walls of the pipe, but also disturbances to the flow path. This causes pressure losses which waste energy from the pump. The amount of friction depends on the liquid type as well as the materials and fittings used. Therefore, we must calculate how much friction or pressure loss our system will generate and ensure that the pump we select can overcome this. Otherwise, we're not going to get any liquid out the other end. When we look at the pump charts, we'll find pumps ranging in head and flow rate. For example, when we look at a small domestic heating system, there are a few fittings and short pipes. Therefore, we would use a pump with a relatively low head pressure. But if we were to look at a commercial heating system with multiple air handling units, fan coils, and long pipe lengths, then we know the pressure drop will be much higher, so we would need a pump that can provide much more head pressure. The flow rate is a measurement of how much liquid is flowing from the pump in a given amount of time. This measurement comes in many different units, for example gallons per minute, litres per second, or cubic meters per hour. For example, a system might be designed to move 2 litres of water per second from a holding tank to a process tank. Performance curve. This is sometimes referred to as the HQ curve. H meaning head and Q which represents flow rate. The manufacturer will test each pump to obtain the performance data and then plot this on the graph. This will represent all the possible configurations between flow rate and head pressure, and we use this to check whether a pump will suit our requirements. The performance curve will be different for each pump, and some will suit our system needs better than others. You will usually see that as the pump flow rate increases, the head pressure decreases. When selecting a circulating pump, the pump will only perform as per the line. So, for this model, if we wanted 8 gallons per minute, then we would have 6 foot of head. You can also get multi-speed circulating pumps, which we'll look at later on in this video. When selecting a larger centrifugal pump, as long as our system requirements are on or below the performance line, then the pump can be considered. We can potentially use a smaller impeller or variable frequency drive to better suit our requirements. And again, we're going to look at that a little later in this video. For example, the performance curve of 2 large centrifugal pumps are plotted here. We need a flow rate of 30 gallons per minute and a head pressure of 70 feet. That means that pump 2 can't be used, but pump 1 could be.
And that's really basically how engineers choose the right pump for, say, a brand new pump station that's being rebuilt. They know in typically gallons per minute or liters per second how much flow we need in order to suit that application. We know from elevation how many meters of head we need, and they would build in to this head calculation things like the pipe diameter and material, and they have formulas to calculate that. And they're just plotted out on the graph. The manufacturer supplies the curve for every pump, and some will have multiple curves based on different impellers. The engineer then chooses the best spot. And again, they want the highest efficiency. And the curves will vary based on the design of the pump itself. But basically, as soon as we know which pump will suit, we can then specify that and build around it. But it's these 2 factors, and that's how we visually space them out. Now, this video goes on to talk about other things, like the size of the impeller that can change based on, within the same volute, how much water and how much efficiency we have. I'm not going to worry about that. You won't have to. But the other part of that is we can now create and overlay horsepower. We can specify the power and the efficiency of the pump and the motor so that we can actually choose how many horsepower based on the size of the impeller. So we have multiple parameters that we can lay out on a chart and then create the right pump for the job. So we won't, just for time, we're not going to go through that. Feel free to take a look at any of these videos, but really what we're looking at when we choose to start with, to choose the right pump, is the head flow relationship, right? HQ, we know flow is Q, is in our hydraulic section, head in meters or in feet. That's critical. And then what we want to do is find the most efficient pump and then the most efficient motor. We would love to get 85% because there is always some loss, some slip. Some water doesn't move to discharge right away. It may circulate a bit. And some motors have the same slip that we don't get full efficiency. But we really, the highest efficiency means for every dollar spent to create kilowatts of energy, we move 85% of the water that we want moved. So here's another example of the curve where this is an American one, so you can see total head in feet, gallons per minute, and you can see based on where, just looking at the HQ curve here, which is this curve here, this pump at 120 feet will pump 1,600 gallons a minute, but only at 120. If you need it to pump 160, well then you better have very low capacity, maybe 800 gallons a minute. Even that's getting dicey, right? So, and you can see as you move closer to zero, yeah, it'll pump 160 feet, little lift, 160 feet, but it's not going to move any water. So we need to know at 1,600 gallons per minute, the HQ curve will tell us we're not really going any higher than 120 feet. And that would include things like friction loss. And then the efficiency out here in percent, 82% based on this efficiency versus flow. So again, 1,600 gallons a minute. Okay, where are we? Well, we don't want to be further down here if we're trying to move too much water or too little. So, all right, we've got a pump that will be basically 85%, 82% effective at 1,600 gallons a minute. And at that point, the power to flow relationship, we're looking at about 60 horsepower. So engineers will look at all that information and overlay it all together to create the right pump and or motor. And also to check, is it the best suited application? And again, the difference between pumps in series, so we basically push water through one pump and then push it, the discharge water through another pump. Here's the curve with one. Oh, okay, we put a second one in. It's almost double. As you get further and further out the curve, the difference is less. But we're definitely adding, right, energy. The flow is the same, but the energy is increased. That's why this line is above the other. Whereas if they're in parallel, we're running water at the same time through two pumps, then basically what we've got is, again, higher flow, but the dynamic head is the same, right? So that's why we only have really this one curve. One pump will move this much water, two pumps this much, but at a much lower head. So engineers can choose how we do that. And of course, the other thing we do with our pump stations is, or pumping systems, is figure out how to control them so that you as an operator don't have to be standing there flipping a switch 24 hours a day. So they can be the controls that are at the station itself, so floats, HOA switches, bubblers, which are basically little plastic tubes that sense the level in a tank, and based on the pressure against the tube, displaces the air and turns on, sends a signal to turn on a pump. Or we can have a SCADA system where we can actually run our water system remotely, either through radio or hardwire. A couple of devices, or a couple of ways of doing that. I've got a 2-minute video that I am going to show you.
Systems track and report pipeline pressure, tank levels, and temperatures. In many cases, the data can be directly integrated into a graphical user interface that can be customized.
So you may be asked, what does SCADA stand for? SCADA, Supervisory Control and data acquisition. So this is a very short video talking about how do we monitor our pump and reservoirs when we're not there.
Optimized and scaled. For example, a chemical storage tank that is almost empty may generate an alarm. A programmable logic controller at the remote site can operate several automated valves to fill the tank. A well-designed SCADA system can perform many tasks to operate a treatment facility and distribution system. The SCADA system may initiate pre-programmed responses to contingent alarms at remote stations. And while the SCADA can be programmed to react to different events, ultimately, it is the operator who must monitor and use the information being provided by the SCADA system to make important water quality and/or quantity decisions. There are two different types of SCADA users. The first group is the traditional SCADA user, process and equipment operators who require real-time information to monitor and control critical treatment processes. A second group of users who need to view and analyze the data for planning and decision-making purposes. These are often managers and supervisors. Utilities can harness SCADA systems to reduce operating costs, automate operations, and facilitate compliance reporting. Automating these tasks eventually may require fewer, better-trained, technically savvy operators to leverage the full power of a water treatment or distribution SCADA system. SCADA has become popular as a key component for system control, but has since evolved to monitor water quality. The development of dependable chemical sensors has led to the use of SCADA as a valuable tool to monitor and control water quality. Calibratable sensor heads provide data to the system, directly or remotely. These sensors can measure many water quality parameters such as pH, oxidation, reduction potential, conductivity, dissolved oxygen, turbidity, particle count, ammonia, total organic carbon, ozone, and chlorine residual. This information is invaluable to the operator's monitoring of water supply. And with real-time monitoring, an operator can make timely adjustments that might have taken hours or days before due to travel, manual data collection, and individual laboratory testing.
So one of the issues around SCADA today is versatility, and we're able now with SCADA systems, and some of you may have them, where they're actually brought to your phone. So you have the information of what's happening at your pump station right on your phone or reservoir. And you know, in the old days, sometimes SCADA systems were just simply called alarm systems because that's basically what they did, is they sent out an alarm when something was out of cycle, whether it was a pump failing to start or a motor overload or a water reservoir level too low, or say a backup generator doesn't turn on when it's supposed to. You may be asked what the actual abbreviation stands for: supervisory control and data acquisition. But they allow now remote control as well as supervision of many sites simultaneously over large geographic areas. And typically the RTU, or remote terminal unit, or the programmable logic controllers are actually running the station. They sense the failure or fault or condition and report back. And gather historical data is how the system works. So here's an example of basically server, slave terminal, and then basically either through radio or telephone system or satellite now coming back in to let the operators know how the system is functioning. One of the issues too is now that they're all web-based, they used to be hardwired dedicated system. There have been a couple of situations where on the news where a small water system in Florida, someone hacked the SCADA system and actually added chemicals into the water supply when they shouldn't have. The operator got the alarm that the, I think it was sodium hydroxide was too high and was able to shut it down. So yeah, there's benefits from it, but also risks. But the ability of the technology now to tell an operator what's happening at a pump station or at a reservoir is amazing, because of course it saves the operator from having to go to the site to diagnose the problem. All right, just a quick couple of questions of review. So again, the packing, if we're using rings of packing, how many degrees should the joints be staggered? 90 to 180, basically the correct answer we're looking for is in that 90-degree range. What type of pump has high efficiencies at very high pressure? Impellers that are very close fitting and high maintenance costs. Mixed flow. They're also, it's interesting because they're also vertical turbines because they're asking two different questions at the same time. High efficiency, high flows, and high pressure would be the vertical turbine. High maintenance costs would be the mixed flow. Which type of pump has rotating impellers within a pump balloon? Well, what they're looking for here is the the centrifugal pump. Total dynamic head, well, those were those two schematics that I was showing you. Basically, we want the best answer here. Can't be static head and suction head. We're not subtracting head losses. We have to add head losses to create dynamic head. Dynamic head is that elevation that we have to design the pump for to cover not just the discharge head, but the head losses. So we're looking at that. Dynamic head is best described as discharge head plus head loss. What type is most often? Well, they're looking at the velocity. Remember, velocity or kinetic is also, in shorthand, we talk about it as a centrifugal pump. Whereas a piston pump and the Archimedes screw pump are examples of positive displacement pumps, which are typically smaller flows and specialty applications like metering or sampling or disinfection, that sort of thing, dewatering and so on. Oh, there it is, last one. All right, so what I'm going to do, see if I can quickly find the file to share, the PDF. I will share that with you. And then you can be on your way. Next week, we're going to talk about some of the keys for O&M. Where is it? Pumps and pump related. Pumps and motors. There it is. Okay. So that should go to everyone. So there's the PDF for today. Oh, question. Yes, I think I should be able to send you the questions for this week and the answers for last week. So, and then we will see you next week. Let me just quickly send you those two files since you're here now. And so next week will be O&M. And then, as I mentioned, we will do the review. And hopefully then you're all set to go for the questions for this week. And the answers from last week. Okay, so there you go. You've got all the files. So the PDF and the two questions, the answers from last week and the questions for this week. So have yourselves a great week, evening/week, and we will see you on the 31st.
Right. Thank you very much, Mike, and have a great evening. And
All right.
thank you again. We see you next week.
Next week for sure.
Right.
Okay. Take care, everyone.
Take care. Bye-bye.